Today I want to talk about reciprocal lattice, and as an example I will consider like some examples in 2D, and I'm going to spend some time to sort out the details about the graphene reciprocal lattice. Okay, let's start. First, we consider functions with translational symmetry of the lattice. We consider functions with translation of crystal lattice. As an example, we can consider like electronic density. Let's take 1D for simplicity. Rho of x is going to be equal to rho of x plus a, and it's going to be equal to rho of x plus na. Right? So this is 1D example. Is small note, like given any function f of x, which could be like, for example, atomic density, right? The density of a localized atom on the crystal lattice, and we can form a periodic function from this by like periodically shifting over all possible lattice sites. So this is going to be f of x minus na, where n is element of lattice sites. And the example is, let me illustrate that. So suppose I have this function. I have this function at some point. I don't know, this is like, let's say this is x is equal to 0. And we just basically translate it in all possible ways. And resulting summation and dot 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 and dot dot dot, it's going to be periodic. So in general, we need periodicity of observables, and let me write it like this. Any observable, let's say density, is going to be equal to rho of r plus r for all r in lattice. And if a function is periodic, we know like Fourier transform works. Fourier transform is the ideal representation of periodic functions, like for Fourier transform. And in the case of rho of r, we can consider g rho of r e to the I g dot r, and using this to be equal to this object, we can just translate also the Fourier transform. So this is going to be r plus r. So let me spell this out, and this is going to be e to the I g dot r, and for rho of r to be equal to rho of r plus uppercase r, we require this piece to be equal to 1. Then we need g dot r should be equal to 2 pi up to some integer. Let me call it like z. But the lattice vectors are defined like they are defined like some n1 a1 plus n2 a2 plus n3 a3. This suggests if we have g dot any lattice vector aj equal to 2 pi mj for some mj element of z, and j is equal to 1, 2 or 3, the periodicity condition will be satisfied. Note, if G1 satisfies this condition, some let me call it AI, MI, let me call it MJ, like 2 pi MJ, and some other vector, let's call it G2, also satisfies with some other integer, then G1 plus G2, actually also G1 minus G2 and their sum also satisfies, they are also is equal to 2 pi mj plus mj prime, which is also an integer, right? But this is the condition for a Bravais lattice. Then is called reciprocal lattice. So if you remember, in the real space lattice, given a lattice, we form the entire lattice structure from some primitive lattice vectors. Then here we need to construct primitive lattice vectors of these G vectors similar to R vectors. So there is like a procedure to do this. Let's, like, if you remember, A1, A2 and A3 are primitive lattice vectors, and let B1, B2 and B3 be vectors of reciprocal lattice. Then the procedure is B1 is equal to vector 2 pi A2 cross A3 divided by A1 cross A2 dot A3, and similarly for 2 and 3, this is 2, this is 3 cross 1. I just cyclically permutate, and B3 is going to be 1 and 2. Therefore, it is easy to see any BI dotted with any AJ is going to be 2 pi delta IJ. Right? Because, for example, if you take the inner product of, for example, let me just show one example. Example b1 dot aj is going to be, let's copy this, is equal to this is aj, but a2 cross a3 is going to be perpendicular to both a2 and a3, and if j is equal to 2 or j is equal to 3, this is going to be 0. The only possibility is this one is 1, but when this is 1, numerator and denominator are the same, and this is going to be 2 pi delta, actually let's keep it general, j delta 1 j, and the others follows similarly. Now the most general R was N1 A1 plus 2 plus N3 A3, and we can write exactly a similar expression for a reciprocal lattice vector. G, the most general G, is going to be some V1 B1 plus V2 B2 plus V3 B3. Here all Ni and Vi are integers. And now we can consider G dot R is going to be, okay, so this A1 dotted into B1 is 1, but A1 dotted into B2 is 0. This one is 0. So only this only the direct terms are going to contribute, and this is going to be N1 B1 plus N2 B2 plus N3 B3, and this entire thing times 2 pi. But these are integers, and product of integers is also an integer, and sum of integers is also an integer, and this entire thing is an integer. Then the condition that we required in the beginning, this condition is satisfied. Lastly, one type of unit cell we described earlier was Wigner-Seitz cell. Wigner-Seitz cell was a unit cell that was centered on a site, and we can also define a Wigner-Seitz cell in the reciprocal space, and it has a special name. So Wigner-Seitz cell in reciprocal space is called Brillouin zone. Okay, now I want to go through some examples. So examples. Let's start with the simplest possible lattice. So 1D lattice. So Rn is going to be some n times A. It's going to be something like that. And the difference between each lattice side is A. And reciprocal lattice is going to be G. Let me also use n for this. And it's going to be 2 pi over A times n. And it's also exactly the same. The only difference is the distance is 2 pi over A. And let's construct the Wigner-Seitz cell of the reciprocal lattice. So in the Wigner-Seitz construction, I take a line to nearest neighbor and put a perpendicular bisector right in the middle. So suppose I'm taking this side and I take another line to another nearest neighbor and I put another perpendicular bisector in the middle, and the region enclosed between these two is called Brillouin zone. And here the boundary of, okay, if we take this central side to be 0, the left boundary of the Brillouin zone is going to be minus pi over a, and right boundary is going to be pi over a, and the length is going to be 2 pi over a. Let's consider a 2D lattice with primitive vectors. Let's take a1 equal to a1 times x, and a2 is equal to a vector a2 y. Let's for generality, let's take a1 be unequal to a2. Actually, let's assume a1 is bigger than a2. Then what we are going to see is, like, here is central side. So this is a1. So this is a2. And the other sides. Then reciprocal lattice, like b1 is going to be 2 pi over a1 x, and b2 is going to be 2 pi over a2 y hat. And since a1 is bigger than a2, 1 over a1 is going to be smaller than 1 over a2, then the reciprocal lattice is going to be something like that. So this is 2 pi over a1, this is 2 pi over a2, so there's like a side here, there's another, and similarly on that side. Now let's construct the Wigner-Seitz cell. So find the distance to nearest neighbor, draw like a perpendicular bisector, another one here, another one here, another one here, and this area is Brillouin zone. So as an exercise, construct reciprocal lattice for 2D triangular lattice. And here, if you want, this is going to be the unit vectors are not, there's no unique vector choice, but you can choose something like that. This is a dot x. So this is, the length is also a, and this angle is going to be 60 degrees. If you want, like, a1 is going to be a times x, and a2 is going to be a over 2 x hat plus root 3 over 2 a y hat. But I am not going to do this. I will do something related. I will do the construction for graphene, because we are going to be using graphene a lot in this course. So let's consider graphene. So last week, as we mentioned, graphene is what we call a non-Bravais lattice. So let's draw like, and it has basically 2 atoms per unit cell. Let me call one of them blue, and the other one red. And this is the bond. And I want to consider this and this. Let me try to translate. Maybe like this. Maybe another one here. Maybe another one here. Something like that. So I want to consider these nearest neighbor vectors. So this one, let me call this one delta 1, this one delta 2, this one delta 3. So delta 1 is going to be, okay, I may sometimes forget to put arrows. Delta 1 is going to be A times 1, 0. This is the nearest neighbor distance. I will call it lattice. It is not actually lattice constant, but let me call it like the nearest neighbor distance. Delta 2, so this one is going to be equal to A times minus a half root 3 over 2, and delta 3 is going to be equal to exactly the same thing, but with one more minus. And for the primitive basis vectors, they are not unique. I'm going to choose, you can choose others, but I'm going to choose these. So this one and this one, let me call this one A1, this one A2. And I can calculate A1 and A2 in terms of delta 1 and delta 2. For example, and delta 3, A1 is going to be equal to, you can kind of see this is going to be, if you flip this and sum delta 1 minus delta 3 is going to be A1. Delta 1 minus delta 3. And that one is equal to A times 3 over 2 root 3 over 2. And similarly, actually let me just copy. A2 is going to be delta 1 minus delta 2, and it is going to be, I think this one is plus, this one is minus. Now we need to construct reciprocal lattice vectors. Reciprocal lattice vectors. B1 is going to be equal to 2 pi over BC. Okay, I am going to, like, there are like 2 basis vectors, and I'll consider a third basis vector out of page, and it's going to be unit length. And in terms of this unit length vector, I can define B1, B2, and B3 as, so this is going to be A2 cross Z, and B2 is going to be 2 pi over VC Z cross A1. And here this V is the unit cell size. V of VC is A1 cross A2 dot Z. And let me just take absolute value So VC is equal to, okay, this is that, A1, so this is A3 over 2, A root 3 over 2, 0, and A2 is same as that one but with a minus, and I'm going to get Z component absolute value, and this is going to be A square 3 root 3 over 4. Okay, this is minus 3 root 3 over 4, and I'll take the absolute value because volume is positive, and this one is going to be A square 3 root 3 divided by 2. Let me check that. Yes, that's correct. Now I want to calculate A2 cross C. And A2 is, I think, this one. And Z is 0, 0, 1. I'm going to be X, Y, and Z. And this is equal to, so minus A root 3 over 2 X minus, okay, there's also A here, 3A over 2 Y and 0. Let me check that. 2, 3 over 2 minus A 3 over 2. This seems to be correct. And lastly, I need to calculate Z cross A1, and it is going to be 0, 0, 1, and A1 was equal to this one. Here, bring that here. This is X, Y, and Z, and this is equal to 0 minus A root 3 over 2 X hat. Close this one. This is 0. Minus minus is plus A 3 over 2 Y hat. Let me check that. C cross A1 minus A root 3 over 2 A. Okay, this one is also correct. Then now I can put all of these in the definition. This is 2 pi over the unit cell size is this guy and this one, and B2 is going to be equal to exactly the same factor but this one. And I like to put like this 2 factor of 2 pi over A because that's the Brillouin size from like a one-dimensional case. I want to put that in front. So cancel this with that and that. Cancel this with that and that. Let me write this like 2 pi over A. So these two cancel, these two cancel, and it's going to be, if I push this, it's going to be minus 1 over 3 X hat minus 1 over root 3 y hat minus 1 over t. Yeah, this seems to be correct. And this one is going to be 2 pi over a minus 1 over 3 x hat plus 1 over root 3 y hat. Okay, let's draw this. So in units of 2 pi over a, so I have something like 1 over 3. So this is minus minus. Okay, let me just write this. I need to draw this one and this one. So this is minus 1 over 3 and minus 1 over root 3, and this one is the same thing, but y component is flipped, something like that. And if I sum these two, this is also a reciprocal lattice vector, so it's something like that. If I take the minus of this, this is also a reciprocal lattice vector, it's something like that. And the same thing here, if I take the minus of this guy, it is also a reciprocal lattice vector, and same as here. So there is a side here, another reciprocal lattice, another point, another point, and another point. Now let's try to construct the Wigner-Zeit cell. So put the perpendicular bisector in the middle, another one in the middle here, another one like this, another one here, another one here, and another one here. So it's a little bit crooked, but it is like a hexagon with the corners on top and bottom, and the real space was like a hexagon, the corners was like this. Basically reciprocal lattice unit cell is just rotated by pi over 2 as before. So these points, so this point and this point are special. This is like so-called K, and this is K prime points. And by symmetry, if this is K prime, this is also K prime. This is K, this is K prime, and this is K. And you can use a little bit of geometry. You know this vector, so this vector is, for example, in units of 2 pi over a, this is 1/3 comma 1 over root 3. This is minus 1 over 3 minus 1 over root 3, and some of this point is 2 over 3, 0, and so this angle is 60 degrees. You can use a little bit of geometry to find this K point to be 1 over 3 comma 1 over 3 root 3, and K prime to be, okay, this is in units of 2 pi over a, and this is 1 over 3 minus 1 over 3 root 3 in units of 2 pi over a. Right, that was the Brillouin zone of hexagonal lattice, like graphene, if you want. Right. Let's take a break. Thanks.